Hey friends, it's good to be back with you. Today we are going to drop the C-bomb. We are going to start on calculus, and we're going to start with derivatives. Now, before we start with derivatives, before we start learning the mechanics of it, which actually aren't that hard, we need some motivation. We need to figure out why we're doing this. Now, I have no doubt that you are conscientious, hardworking, and will diligently apply yourself to your studies. But without some innate understanding of why you're doing it and why this is important and why it's worth retaining, you're going to get through all the graded exercises that might be in front of you. And then when you're done, you're going to walk out and just do a little bit of this, and all the ones and zeros that are in your brain are going to come out, fall on the sidewalk, and you're just going to walk away, and that'll be the end of derivatives. That's not such a great outcome, is it? If we're going to put all this work into learning it, we need to know why. Now, a derivative is just a slope. There's nothing more to it than that. There's no hidden meaning. There's no deeper truth to it than that. It's just a slope. More specifically, it's the slope of a curve. Well, what's that look like? Well, let me draw one here. Let's make this axis time, and maybe let's make this axis velocity. Okay, how fast you're moving. Velocity of what? I don't know. What's something that really changes velocity quickly? How about an airplane getting shot off the end of an aircraft carrier? I've obviously never done it, but it looks pretty violent. So what does it look like? I don't know. How about that? Well, it turns out acceleration is the slope of velocity. Why? Well, because Newton defined it that way. So at any given point, let's say, I don't know, let's see, the end of the catapult must be right about there, and then the engines take over. Well, we can figure out what the acceleration of the plane is by looking at the slope of the velocity, the rate of change. Okay, that's a derivative. Derivative's just a slope. Okay, well, that's the definition, but it still doesn't address why we care. I mean, we care a little bit here because we care about acceleration, but that's only a specific case. Let's look a little broader here. Here's what I'd like you to do. Now pause for a moment and try to think of any physical law that does not include a slope. Ready? Go. Well, what are some of them? Oh, let's see. Dynamics. Well, Newton developed calculus in part to study dynamics, so of course that obviously includes slopes. Aerodynamics? Well, the Navier-Stokes equations have slopes all over the place. How about electromagnetism, which includes optics? Yeah, slopes everywhere, derivatives everywhere. Thermodynamics? Yeah, derivatives everywhere. General relativity? Boy, tensor formulations, there's slopes everywhere there. Oh gosh, how about some others? Acoustics? Yeah, derivatives everywhere. You take the point. Any physical law that you want to work with has to be written out mathematically, and if there's one that doesn't include derivatives, doesn't include slopes, I can't think of what it would be right now. I'm hedging on quantum mechanics. I know next to nothing about it. Does quantum mechanics include slopes? Yeah, probably, but I couldn't tell you how. I bet it does, though. So the point is, derivatives, not only are they everywhere, they seem to be woven into the fabric of creation. How about that? Is that big enough for you? If you don't understand derivatives, you can't describe anything around you mathematically. Whew, that's big. Okay, so with that in mind, let's get started here. I'm going to erase this. Let's maybe start with Newton's use of derivatives. Now, calculus, if you read certain historical articles or books, it may sound like calculus just popped up out of nowhere. Well, it's not quite true. People had been sneaking up on derivatives and integrals for quite a while, but they were in a very crude form in the, I guess it would have been about the late 1600s, I think. Newton was born in 1642, so it would have been the late 1600s. Gottfried Leibniz in Germany and Isaac Newton in England were both developing what we now know as calculus. And they were doing it independently. Now, did they know about each other? It's hard to say, probably, but not in detail. So they both started describing calculus publicly, Newton in his great work Principia Mathematica, and Leibniz in some other places. And unfortunately, they spent the rest of their lives in an argument about who had priority. In hindsight, it looks like they both worked more or less independently. I think Newton probably gets more of the credit. I guess that's okay. The reason I'm telling you this is that they have different notations. Newton's notation and his terminology was extremely difficult. I'm not sure he intended Principia Mathematica to be hard to read, but boy, it's a hard read. Leibniz had this quaint idea that if people understand his ideas, they might use them. Wow, nutty, but there it is. So we have two different notations, at least, for derivatives, and I'll try to reference both of them. Okay, so we're just talking about slopes here. Well, Newton, one of his great insights was to say, well, let's say I have position as a function of time. Whoops, spell that right. There we go. And I'll call it f of x. Sorry. And I'll call that x of t. All right, position is a function of time. Well, I care about position. I also care about velocity. Well, let's see. Velocity, that's the rate of change of position. Okay, as position changes with time, that's velocity. Well, how do you write that? Well, one way to do it is to write it as x dot. And that dot signifies a derivative with respect to time. Sometimes you'll also see a little line, like a single quote after that. By tradition, that signifies a derivative with respect to position rather than time. But for right now, we're looking at rates of change of time. So we're going to use that dot. One dot is a first derivative, second dot is the derivative of a derivative. So another way to write this, oops, is this way. And this is actually a little more, what a bad morning here. There we go. Another way to write that is dx dt. And this is actually probably a little more informative. This is harder to write, a little more cumbersome, but more instructive. So I'll use that most of the time. Well, that says the change in position as time changes. And those d's there are really important. We'll look at those in a minute here. But that's enough to say this is the slope of position. That is, if we were to plot position with time, as sort of like I did before, only position instead of velocity, the slope of that position is the velocity. All right, well, let's keep going. Let's define acceleration. Well, that'll be x double dot. All right, that's the second derivative of position. It's the derivative of a derivative. We could say it's the rate of change of velocity. Because if you're accelerating, you're changing your velocity, so we can write it that way. We can also write it as the second derivative of position, the derivative of a derivative. And this is okay too. These all mean the same thing. Now, there's a little bit of terminology going on here. The double dot means second derivative. There's the first derivative of velocity. All right, here's the second derivative of position. Well, there's a 2 right there and a 2 right there, and they're in different places. Why? I don't know. There's a couple of explanations out there, but for right now, we'll consider it just tradition. So, second derivative of position is acceleration. First derivative of velocity is acceleration, and there it is. So these are defined by Newton. Okay, this is part of what came out of Newton's groundbreaking work. Let's write this out here just for completeness. Slope of velocity. So that's what this looks like. This is one of the reasons we care. We can write things like this down for aerodynamics, electromagnetism, thermodynamics, relativity, optics, acoustics, yada, yada. Okay, so this is why we care. It's very, very fundamental to our understanding of the physical world around us. If you're going to work as a scientist, an engineer, anything like that, you have to understand this or you're just dead in the water. All right? So with that, I've been kind of dancing around this. What is this exactly? What does this mean? All right? And I said it's the slope of position. Well, slope? We learned that in, I don't know, junior high school algebra maybe? Let's take a look at that. Okay, if I want to find the slope of a line and I have 2 points along the line, let's just do this. And I'll make this x and this y. These will be slope with respect to position, all right? Now, hang on a second. What do I mean by slope? I've got a board here I was using for other things, and it's got magnets in the back of it, so I can stick it right there. Well, that's pretty much horizontal, isn't it? Slope of that's 0. Let's see if I move it. Let's see if I can get it to stick there. It looked pretty close to 45 degrees. That slope is -1. There we go. That slope is infinity. Okay, let's try this. A million years ago, a teacher somewhere, probably Mrs. Miller at Longfellow Elementary in Bozeman, Montana, told me that slope equals rise over run. And I don't know if they still use those words or not. That's as good as any. Rise is vertical, change in vertical position, and run is change in horizontal position. And they both start with R, so when you're 9, this is pretty easy to remember. So how are we going to do that mathematically? Well, let's do this. Let's call that position x1 and that position x2. And there's 2 points along this line. Okay? The slope is defined between 2 points along a line. That's where slope comes from. I don't know of any other definition. That's terrible. That's a little better. Okay, so that's y1 and that's y2. All right. Okay, this is from the Greeks, really, because the Greeks did everything with a straight edge and a compass. So this is probably Greek. That's the definition of a slope. I guess that should be a dashed line, shouldn't it? There we go. Do a little editing after the fact. So that looks pretty good. So slope, if it's rise over run, okay, how about y2 minus y1 equals x2 minus x1? All right. Well, that's rise, that's run, isn't it? I don't know what else it would be. And I also don't know of any other definition of slope, at least not one that means anything. This is all we need. So far, I mean, we're in junior high school here right now, okay? This isn't that hard. Well, we're going to make one very small change. That distance right there, we're going to call delta x just because it's going to be more convenient to do it that way. And capital delta, when we use that in an equation, most of the time that means a change in something, and it means a specific change. We know what the change is. We can assign a number to it. So when you see that capital delta there, that's normally what you mean. So I'm going to write out that, okay? That's the slope. I mean, I don't know of any other definition that means anything. Are we done? Almost. Okay, so far so good. I don't know if this even rises to the level of algebra. I guess it does, but just barely. Okay, let's turn this from algebra into calculus, and it only takes one more step. I'm going to erase this. Now, things in the real world, things in the physical world around us are changing all the time. Historically, Newton was really interested in what happened as planets orbited the sun. Because planets orbit in ellipses, almost never a circle, it means the distance from the sun is changing all the time. Since the gravitational force is dependent on the distance from the sun to something orbiting it, that means the gravitational force is changing all the time. It's a curve. So in order to figure out how to mathematically describe the forces on a planet as it went around its orbit, he had to have some way of thinking about quantities that changed smoothly and continuously. That's where derivatives came from, at least in that case. So how do we write this out mathematically? Well, let's draw it first. Let's say there's x and there's y, and I've got some curve here. doesn't matter what it is, but let's say it looks like that. And we'll call that y of x. Right there, that's that curve. Right? And we want to know what is the slope at a point. Now that's the big question. I want to know the slope of this curve at a point. Why? Well, maybe I want to know its velocity. Maybe I want to know its acceleration. Maybe I want to know how the force of gravitational force is changing as a planet moves through its orbit around the sun, some larger body. There's a lot of reasons I might want to know this, but we do want to know the slope, and I want to know it at a point. Say I want to know it right there. Well, how are you going to do that? Well, let's see. I could call that x1. Now, I need to go out a little ways in order to draw a slope. Slope is between 2 points. There's no other definition that I know of. So let's do this. Let's just make another point out here, x2. That, just like we saw before, that's y1, and that's y2. Now this slope happens to be positive. The one I drew before happened to be negative. It doesn't really matter. And let's just say that the slope is approximately, that's when you put an equal sign with that little tilde over the top of it, that little squiggle, that says approximately equal to, and that's really important here, really important. Now sometimes you'll see it written that way, and sometimes you'll see it written this way. Let's write it this way because that's what's in Word actually. Okay, so that squiggle means that's approximately equal to, well, let's see, y2 minus y1 over delta x, with that being delta x. All right. How approximate is it? I don't know. It depends on how far that is. If that's and that's a big distance, well, this may not be too good. Well, how do you make this better? Well, the closer those points are together, because right, what I got right now, let's zoom in here. Let's go down here. If there's my curve, and there's my points, let's see, x1, x2, I'll get my head out of your way here in a second. Just let me do this. Okay, there's the curve I've got. Well, what's my approximation to it? Well, approximation, let's see if I can do this, is going to be that. That's the approximate slope. Well, you can see that it's close. That's pretty close. It's probably close to exact right in there, in the middle somewhere, but it's not quite right there, and it's not quite right there. Well, how do I make this a better approximation? Well, let's get rid of that. Let's get rid of that. And let's just move this in really, oops, wrong color. I gotta get rid of that too. Let's just move this in really close. Okay, there's x2, and there's my new y2. Okay, well, is that a better approximation? Fix my curve here. Is that a better approximation? Yeah, that's a lot better. That's a lot better. The error is much smaller. It's still approximate, but it's a lot less approximate. But it's still not exact. Dang. All right, here's the big idea. Where we've walked up to it. It's sitting right on the ground in front of us right now. How small can this be? I'll call that delta x, as I did up there. How small can delta x be? Can it be 0? No, you're not allowed to divide by 0. That's undefined. How small can it be? And this is what turns algebra into calculus. How small it can be is infinitesimally small. And this is the idea that hung everybody up. This is the idea that people struggled to accept. Infinitesimally small means so small it doesn't matter anymore, but not 0. Well, what value is infinitesimally small? It doesn't have one. Infinitesimal is not a number, it is a concept. So, all the engineers among you are now getting the existential willies. What do you mean it's a small number, but we don't know what it is? Is it a millionth, a billionth, a trillionth, 10 to the minus 37? What is it? Well, we don't know. But it turns out we don't have to know. That's the big idea here. So what I'm going to do, I'm going to erase this to make some more room. And I'm going to make one change to that expression right there. And I'm going to turn it into a derivative. So I'm going to do that. I'm going to leave this. This is still true. And I'm going to write this thing here. The limit as delta x goes to 0, that's the derivative. All right, that is the definition of a derivative. There is no other definition. Well, none that you need to care about. There are some more advanced ones, but this is the big one. This is always true. All right, so what does that mean? Well, we're going to let delta x approach 0 but never get there. It doesn't make me feel good. Well, hang on, let's try this. If you've taken calculus before, you may know what how to write down a derivative of a simple function. So what's the derivative of x squared? Okay, you may know that the derivative of x squared is 2x. Why? I mean, it is, you're right. Let's try this. What am I going to do? Can I do this over here? You guys can see this. Let's say y of x equals x squared. Well, without thinking at all about what, the sort of the existential meanings of all this, let's just do what this says. Let's just follow the rule and see what happens. So let's see. If I say the limit, all right, of delta x goes to 0 of that, all I'm going to do is plug that in everywhere I see a y. Now, but how am I going to do this? Let's do this. That's x. This is also x plus delta x. That's x2. x2 is x plus delta x. So now that I know, I'm going to replace that, and I'm going to say x plus delta x squared minus x squared. So that's x1, that's x2. All I have done is just blindly plug in these two x's for that. That's all I've done. I don't even know why. I'm just doing it. I'm just following the rules to see what happens. And I'm going to just put a delta x there. Make that a better 2 because that looks terrible. There we go. That's less terrible. All right. And I guess I kind of ran out of space here. Okay, I put that there to make it an actual equation. Okay, let's just multiply this out and see what happens. So far, this is just algebra, isn't it? I'll do something with that in a minute, but let's just multiply this out. So that's x squared plus 2x delta x plus delta x squared minus x squared. Get my board out of the way. All right. We're still in algebra land here. Let's just do what the algebra says. Well, let's see, x squared minus x squared. That cancels out. All righty. Well, there's a delta x in all those terms, so let's start canceling some of those out. That, and get rid of that 2 there. And so I get limit, that's terrible m, see if I can fix that. That's better. 2x plus delta x. All right, now those of you who have seen this before, you can maybe see where I'm going with this. Does this delta x exactly equal 0? No. Does it get so small that it is irrelevant, that I don't care anymore? It is so small it has no measurable effect on the outcome. Yes. All right. That's not exactly 0. It is infinitesimally small. It's effectively 0. And I get, I'm going to write this out in a little bit more formal way for you here. There. There you go. Look at that. The derivative really is 2x. Now, those of you who've seen this before, which I assume is most of you, when I asked you what the derivative of x squared was, Did you, in your brain, your mind, were you going through all this? No. Say, well, let's see, I know I subtract a 2 from there and push or subtract a 1 from the 2 and push the 2 down here to get that. Now, let me ask you something. I sound like I'm from Philadelphia. Let me ask you something. Did that feel like calculus, or did that feel like algebra? I mean, I know it's calculus. What did it feel like? That felt like algebra, didn't it? Here's the big idea. My office door's closed. It's a Sunday morning, so nobody's around. I can tell you this. Once you know what that means, once you know what an infinitesimal means and you can start working with it, calculus and algebra, they're the same thing. Huh. All right? So if it feels like algebra a lot of the time, well, that's probably right. Now, do you have to go through this every time you're working with the derivative? You have to go through this formal derivation. Blah. No. Fortunately, people have been doing this since, well, the late 1600s, I imagine. And there are tables of these derivatives. There are general rules of how to work with derivatives of functions. And derivatives are pretty straightforward. There's only about 2 or 3 rules you've got to learn. One is called the chain rule. One is called the product rule, and one is called the quotient rule. Well, it turns out the product rule and the quotient rule are basically the same thing. So there's really only 2, chain rule and product rule. That's it. All right, so it's pretty straightforward, and it gets better. It still is getting better. This is a great day. It turns out MATLAB can do this too. MATLAB can do this stuff symbolically for you, right? So with that in mind, let's just go see how MATLAB handles this.